Okay, so good morning, good afternoon, good evening, everyone. My name is Wang. I'm a third-year PhD from the Statistics Department of the Wharton School at the University of Pennsylvania. So today I'm going to talk about this work, The Price of Competition, Effect Size Heterogeneity Matters in High Dimensions. This is a joint work with Jian Chung, who is my fellow PhD student, and my advisor, Wei Jie. To start with, let me briefly talk about the settings. We're considering the high-dimensional linear regression, where we have n observations, and for each observation, we have p features. So an important question of great practical value is how do you do the model selection? How to select a good subset of those p features? And one might concern, how hard is this model selection process? And an intuitive answer, as long as the signals are large enough, for example, under the beta mean conditions, is that the hardness of model selection depends essentially on sparsity. But the use of this word intuitive might already give you a clue that maybe there's some other notion is as important as sparsity in deciding the hardness of model selection. And I will elaborate on that in the following of my speech. Okay, so before we talk anything in detail, let's first talk about the performance criteria that we use to evaluate a model selector. And it turns out that a good set of criteria are the FDP and TPP, the false discovery proportion and the true positive proportion. So to start with, we define the relevant variables, or I will say signals, as those variables that have non-zero coefficient in the true model. And we will define the discoveries as a model select as some hyperparameter level lambda as this S hat. As those variables that have non-zero regression coefficients. With those two terminology, we can actually define FDP and TPP. FDP, intuitively speaking, is a type 1 error, and TPP is a kind of power. The false discovery proportion is just defined as the ratio of number of false discoveries among the number of all discoveries. And the definition of TPP is just the ratio of the true discoveries among the all true variables. So that is the criteria. And let's talk something more about model selection. I think it is without any doubt that in high dimensions, Lasso is the most popular method to do variable selection. And it is also not hard to conceive with this kind of common belief. That is, with the sparsity fixed, the stronger all the signals are, the better a model selector, for example, like Lasso, will perform. Because this is really the intuition of our statisticians. Right? But my question is that, is this kind of common belief really the case? Let's see a two example. Here, I have 4 settings of simulations. And in all of the settings, the design matrix are 1,000 by 1,000 with entry of RID Gaussian variables. And the sparsity are set to be equal to 200, with some weak noise set to be 0.01. Only difference among those 4 settings are the structure of the signals. So we have 4 plots here. And for each plot, the horizontal axis denotes the index of the signals. So we have 200 signals. Here is the signal 1, signal 2, up to signal 200. And the vertical axis denotes the magnitude of each signal. So in setting 1, which I termed the strongest, is all the signals are set to be equal to 200. And setting 2, which I term as strong, even though there have some signals set to be equal to 200, there are some of the signals have magnitude around 100. So this, even though it's also strong, it's weaker than setting 1. And similar reasoning, setting 3 is even weaker, and setting 4 is the weakest among the 4 settings. So one point I want to emphasize is that among those four settings, given our common belief, we would expect that the first setting will give us the best performance because the signals are the strongest overall. And the setting 4 will give us the worst performance. So let's see what is the real result of our simulation. So first of all, I only drew the plots of the weakest result. So this plot, to best appreciate it, you need to understand it is a TPP versus FDP plot. But recall that our definition of TPP and FDP are only two numbers. So how come here we have a curve? So this curve is due to the variation of lambda. So suppose at first you have a lambda that is around infinity. That lambda is too large for Lasso to make any discoveries. So virtually you have 0 power and 0 type 1 error. So you have something here. And with the decrease of lambda from infinity down to 0, more and more variables will enter your Lasso path. So gradually your TPP, your power will increase with the decrease of lambda. And it is also not hard to believe that with the increase, with the entering of all those variables, you are making more and more mistakes. So FDP is also increasing. One observation here is that this weakest curve is not perfect because this point, 1, 0, is not on the curve anywhere. This curve corresponds to full power without making any type 1 error. So that is perfect. And it is also known as the model selection consistency. Apparently, this weakest curve cannot achieve model selection consistency. And also another observation is that in this diagram, the lower a curve is, the better the performance is. So suppose there is another lower curve here, then I'm claiming that this curve is better than the existing curve, in the sense that with a fixed TPP level, it has the less FDP, meaning that with same power, it makes fewer mistakes. So as what we will believe is that in the other three settings, the curve will be somewhere here. So let me plot something more. We plot the third setting, which is the weak setting. And those two curves are very close to each other. But if you zoom in and look carefully, you will realize that the current curve is actually every point above the previous curve. So recall that above means worse performance. That is to say, even weak is a little bit stronger in the sense of signal, but the performance as a variable selector is worse. That is kind of surprising and interesting, but maybe that is only due to the randomness, because every point here are just the average of 100 independent trials. So who knows? Let's just plot something more. So now I'm plotting the strong case, where the signals are even stronger. But as you can see, the performance is even worse. And if I plot all of those four settings, you will notice here is actually a clear spectrum. But this spectrum is quite the opposite as what we expected. So that is really interesting. How do we explain this kind of phenomenon? One possible and intuitive explanation is that Lasso prefers weak signals because virtually everything are the same, including the sparsity, except for the strength of the signals. And Lasso performs even better with weak signals. That is really weird. And to my best knowledge, there's just virtually no theory in the existing literature can explain this kind of phenomenon. So let me propose an alternative explanation. That is, Lasso still favors strong signals as what we expected, but it's just prefers signals that are wildly differing with each other. And we will define this kind of diverse structure of signals as effect size heterogeneity. So with everything else fixed, Lasso will perform the best with the most heterogeneous signals. That is the message we want to convey. So instead of this absurd notion of Lasso prefers weak signals, the actual message is that the effect size heterogeneity really matters. Okay, so let us revisit those 4 settings. But this time, I will give each setting a new name. So even though in the first setting, all the signals are the strongest, but it's also the most homogeneous case. And the setting 4 is the most heterogeneous case. And to explain this phenomenon, I will use the heterogeneity of this effect size to explain why setting 4 performs the best. Okay, so before I proceed to our theory, let me give you a very informal and crude summary of the previous theory of Lasso in the literature. So this is the impression that is given the information of sparsity and also the structure of our design matrix, we can actually understand Lasso as a model selector really well, especially if all the signals are sufficiently large, for example, under the beta mean conditions. That is the general impression. But our proposal is actually that the information of sparsity and the design matrix are very important, but simply not enough. We need to know more about the inner structure of the beta, i.e., whether the signals are homogeneous or heterogeneous. So here goes our main result. So we have 4 assumptions. Assumption 1 is that we have RID Gaussian design. Assumption 2 is that we are considering the noiseless case. Okay, so for this one, it's only a technical convenience that we will relax later. The assumption 3 is that we're considering non-vanishing linear sparsity ratio. And the setting 4 is that we are also considering the case in which N and P are linear and comparable. So the theorem goes like this. With probability tending to 1, we will have FDP uniformly bounded between 2 deterministic curves. Okay, that is a very abstract theorem. So I will give you a pictorial version of this theorem. So as you can see, here we have a blue area, which I call the Lasso Crescent, which is the Lasso path can lie in the TPP versus FDP plots. The name of the Lasso Crescent is that this really looks like a curvy moon shape. Right? I want to emphasize 2 observations. The first is that there's a red and a white area here. So this red area is unachievable. So typically, this 1,0 point cannot be achieved. So that means Lasso cannot do variable selection really well. And this white region is also not achievable. Means that even though in the noiseless case, it cannot perform the best, it cannot also perform arbitrarily bad. The second observation is that actually this blue area is bounded by 2 curves. The upper curve, which we have already said is the worst curve, and the lower curve, which is the best curve or the most favorable curve. And the next result we will give is that all those 2 curves are achievable. So to illustrate that, I need to have 2 more definitions. The first definition corresponds to our intuition about the most heterogeneous signals. So it is called the most favorable prior, which in which for each signal you have epsilon chance to be a true signal, and for different levels of the signals, they are actually wildly different from each other, because we are going to consider the case where big M and small m are going to infinity. So this is really a mathematical form of our intuition on the most heterogeneous prior. And the second definition is just the homogeneous definition of the prior, where for all the signals, they are all have the same magnitude set to be m. And here is our theorem. That is the that is the least favorable prior will achieve the least favorable curve, and the most favorable prior will achieve the most favorable curve asymptotically. So let us revisit this Lasso Crescent. As we said, this is the least favorable curve, and it will be achieved by the homogeneous prior. And this corresponds to the most favorable curve, and it will be achieved by the most heterogeneous one. So that means effect size heterogeneity really matters. So let me put some more remarks on our result. The first is that you might notice there's a 0.001 in this theorem, but that is not a magic number. It can be replaced by any small numbers. And the second one is that actually the lower curve is not discovered by us, but is first discovered by Sue, Bogdan, and Candice in 2017. Yet here we are the first to prove that this is uniformly tight and uniformly achievable by some specific prior. And the third one is only to mention that the technical tool that we primarily use is the approximate message passing theory for the proofs. Okay, so that concludes the first part of this talk. And in the next part, we will elaborate on a very different notion of the performance criterion, namely the rank of the false variable instead of using TPP and FDP and more. So we define T as the number of true variables before the first false variable. So let me give you an example. Suppose along your lasso path, the very first variable you discover is something true, and the second one is also true. But with the decrease of your lambda, the third variable that enters your lasso path is actually, unfortunately, false discovery. In that case, T is set to be equal to 3. So intuitively speaking, the larger T is, the better the performance as a model selector. In the extreme case, if your T equal to K plus 1, then you can just simply set the cutoff to be at the Kth point. Then you will just automatically recover the full set of the true variables and achieve model selection consistency. So that is to say, in this case, we expect T to be as large as possible. Okay, and let us review our definition of the most favorable and least favorable prior. And one may have many critiques about those priors. And among them, a typical critique is that, actual signals are not at all randomized, but they should be fixed. So let us consider some fixed signal instead of some randomized prior. And the fixed signal that I will consider is a typical realization of our most favorable prior. That is to say, we will consider the beta that has only K true signals. And for each of those are having very different magnitude. So beta 1 and beta 2 are far from each other, and so is beta 2 and beta 3, and so on. So in this kind of scenario, and when M is sufficiently large, the rank of the first false discoveries can satisfy this inequality. It says that P is greater than this quantity. Okay, so this proposition says something, but it's not a strong evidence of why this kind of signal is the most favorable or desirable one. But fortunately, we have the other direction. That is, we have this theorem. For arbitrary regression coefficient with sparsity not exceeding epsilon, the rank T is actually satisfy an inverse inequality. it is said that for any possible lasso, the largest t is not exceeding this amount. So combining this proposition with this theorem, we can actually say, oh, so this kind of heterogeneous signal is asymptotically the best that we can hope up to some constant factors. So that is very nice, right? And what about the homogeneous case? So here we will invoke a proposition that is due to Su in 2018, where he considered the homogeneous case and found out that the rank actually satisfies this equation, this equality. And it is very easy to compare this result to our previous result and find that in the homogeneous case, the first false discovery occurs much earlier than the heterogeneous case. So let me give you some visual impression about what is the rank of the first false discovery. So I have two simulations. The only difference among those are the design matrix of different size, but the phenomena are the same. So as you can see, with the increase of the sparsity, actually the rank T is first non-distinguishable between the two cases, the heterogeneous case and the homogeneous case. But gradually, after some critical threshold, there's a significant gap between the heterogeneous one and the homogeneous one. So here we can also detect this phenomenon, this gap. And recall that we said the larger the rank, the better the performance as a model selector. So this means that when sparsity is large enough, then the effect size heterogeneity is also going to decide is also going to decide the hardness of model selection. Okay, so now we all know that the effect size heterogeneity does matter, but do we have any explanation? And here is our heuristic explanation, which is termed the price of competition. So to understand this notion, we basically mean that the well-matched or the homogeneous unselected signals are actually competing with each other. And that kind of competition causes the bad performance of a variable selector. So to illustrate by mathematical words, we consider beta hat selected by lambda at some stage. And suppose at this stage, there's no false discoveries. That is to say, S hat still belongs to S. And by KKT condition, we will consider the event that the next variable is actually a false discovery. And it is not hard to derive that that event happens if and only if there is some irrelevant J not belonging to this S have the largest absolute value of this expression. So let's just take a closer look at that expression. So the first approximation that I will do on this one is to replace estimated beta hat by the true signal, by the true beta on the same estimated support S hat. So this approximation is crude and will be problematic if the S hat is large, but let's just take it at first. And I'm claiming that this expression is actually equal to the third expression because we are considering the noiseless case where y just simply equal to x beta. And after some cancellation, you arrive at here. And now you observe that this xg is actually outside the set x. So this is some independent Gaussian vector. If you deem the second part as something fixed, then you will have this whole expression is essentially a Gaussian variable. Now you can do the comparison. In the homogeneous case, you can see that this standard deviation can be read in this form. And because the signals are homogeneous, meaning every signal is the largest and all equal. So these two norms are actually square root k of the largest size of the signals. However, on the other hand, when you have heterogeneous signals, the standard deviation is actually in another form, because the largest signal that you have now selected is the unique largest variable, and no other signals can be even comparable to it. So essentially, the true norm of this expression is just simply 1 times the supreme of the beta gene remains. So when you compare those two expressions, you will realize that in the homogeneous case, the noise have a square root k term to suffer. So we define that square root k to be the price of competition. That is due to the homogeneous effect size, and it will have much larger noise because of the competing of the similar signals. Okay, so let's proceed to the final part of my presentation. Let's just do some reflections on the assumptions. Even though our price of competition and effect size heterogeneity are all proposed and derived and seen in the case of Gaussian design, but it is not hard to believe that this is a general and generic phenomena that occurs outside of the Gaussian region. So we will consider the first assumption. And also, as we have already said, that the noiseless case is only a technical convenience. So we will also relax this assumption. I will show you a lot of simulations, and throughout those simulations, we will stick to those 4 settings of the signal. So remember, the setting 1 is the most homogeneous signals and also the strongest signal. The setting 4 is the most heterogeneous signal, but also the weakest. Now, in the non-Gaussian design matrix, we will observe the same phenomenon. So to illustrate, you can see that on the left, the design matrix is non-Gaussian, and it is autoregressive design matrix with rho set to be equal to a half. And on the right, the design is a Bernoulli design matrix with probability a half, meaning that each entry is set to be equal to 1 with chance half, and otherwise set equal to 0. So even though the shape of those 2 simulation plots are not exactly the same, but you observe the same trend, the same phenomenon, which is that the most homogeneous case is the most desirable case, and the structure is very clear here. And even if we use some real data as our design matrix, we will still observe the same phenomena. So on the left is the HIV dataset, where we have over 600 patients and observed there are over 400 features. And as you can see, this is no longer a smooth curve, but still the same phenomena that the most heterogeneous signal give us the best result. And if you perturb the original HIV data by a random Gaussian noise and then renormalize it, you will have some smooth curve, and you will still observe the same structure, even though there's some irregular peaks here. But the structure is very clear. Still, that the most heterogeneous is the most desirable one. So now let's just relax the second assumption. We want to go from the noiseless to the noisy case and observe still similar phenomena. So in setting 1, we just have still no noise at all. And recall that we have this kind of plot where the most heterogeneous one is the best and the most homogeneous one is the worst. Now, let us inject some noise into it. And then we will realize, oh, it's still the same phenomenon, except there's a critical crossing point, before which we still observe the same hierarchy as we have before. But after that, we notice that the most heterogeneous one is actually the worst. So why is that? Just recall, the most heterogeneous one is also the weakest one. So because we have inject some noise, then at this point, it's actually the signal to noise ratio take the lead. And because the signal to noise ratio for the most heterogeneous one is no longer that large, so it just suffers from being have large noise. So this is the curve. And we will just observe the same phenomena if we inject more and more noise into it. The only difference is that this critical crossing point occurs early and early. So this is the setting where we have large noise, which have still the similar behavior. So to conclude, I have some take-home messages. As always, we think that the effect size heterogeneity is an important thing to consider in practice. And we elaborate its importance from two perspectives: the TPP versus FTP trade-off curve perspective, which we also call the Lasso Crescent, and also the rank of the first false discovery. And we prove that this phenomenon holds under non-vanishing sparsity ratio and under local orthogonal Gaussian design. And we said that the cause heuristically is because of the price of computation of Lasso. And this is inherently just the shrinkage effect of all L1 methods. And given those discoveries, we have some possible future works. So the first one and the foremost one is that because we recall in the noisy simulation, we see that the effect size heterogeneity and the signal to noise ratio both decide the hardness of model selection. So how do we mathematically quantify this effect size heterogeneity? How to quantify this effect on deciding the hardness of the model selection? We actually don't know. And the next one is that because we understand the effect size heterogeneity through those two perspectives, how can we devise some useful and practical methodologies leveraging our understanding through those two perspectives? And the third one is that we have already illustrated that this phenomenon is not only restricted in Gaussian design, and it just applies for very general design. But theoretically speaking, we cannot prove in general design the same phenomenon occurs. So is there any deeper and comprehensive and more comprehensive result that can prove that in very general design, the same phenomenon happens? So the last but not the least, we want to also understand whether the same phenomena will occur in some other method, like in slope and in other L1 methods, whether the same phenomenon, the price of computation and the effect of the effect size heterogeneity matters in other phenomena. All those future works are honestly something that I don't know, that I really want to know. But the most important message that I want to emphasize is that the effect size heterogeneity really matters. And last, let me mention that we will put this paper on arXiv in a week or two. Yeah, and you are very welcome to discuss if you have any questions. Thank you.